Hey everyone, this is Jules Reichelbusch. Some of you may know me as Sound Sleuth. Some of you may know me as DJ Jules from Instructables. And normally I build microphones. Really good microphones to capture the sound of the world around us. And of course, if you're gonna build microphones, you have to have some stuff to listen to it on. And I've recently started getting into immersive audio. My first experience with this is I got a chance to go over to Europe for an AES event in The Hague in the Netherlands right after COVID ended. And I listened to some Dolby Atmos mixes for the first time ever in a room with a whole bunch of speakers. It was phenomenal, just amazing. Then later, I went to a conference on immersive audio in Huddersfield with Professor Hoon-Kook Lee. Once again, these rooms were set up with some fantastic speakers, Genelec ones, cost a lot of money. They're really, really good. And as you know, I like to build things myself and make them less expensive. So, can we build an immersive audio setup, specifically a 7.1.4 setup, inexpensively, that still has really good sound quality? I set out at the beginning of this year to do that, and here are my results. Oh yeah, and the answer is yes, you can. So the first thing I needed was some speakers. I had really had some good main speakers, but I needed the surrounds, specifically for a 7.1.4 setup. You need 7 speakers at ear level, 4 height speakers. So I set out to get some more speakers. Went to Dayton Audio, Parts Express. That's normally where I get all my stuff for things like that. And here's what I found. This is a C Notes speaker. So I built 6 pairs of these because I wanted to be able to take this thing on the road a little bit and demo it. Built 6 pairs of these. Next thing I knew, I would need some amplifiers. The other thing that I did with these that we'll see during the Instructable is I used speak-on connectors so that this thing could set up and break down easily. The room that I have set up at home is a shared space, so I can't just leave all these speakers around, you know what I mean? Some of you may be in that same predicament. So to the amplifiers, I had recently built some Class D amplifiers for a project, and I knew that they actually sounded pretty good. So I went with a couple of these. This is a 4-channel Class D amplifier, and I put a couple of these in a 2 rack mounted unit case and powered them up. If I just used one of them, it sounded great. As soon as I added more, I get this weird interference and it just didn't work. Here's what this sounds like. Yeah, that's not a ground loop, is it? That's something weird. These things switch at a couple hundred kilohertz and there's a lot of EMI generated, and I was getting that fed back into the system. So I went old school with something called an LM3886. I had actually built some amplifiers with these before, something called a gainclone. So that brings us to this little circuit board. That's the actual LM3886 right there, the chip. And some output protection right here. So we needed 12 of these. And they need to mount on heat sinks. So then we end up with 6 of things that look like this, and then they all go into a rack case with a toggle switch to turn it on and off, and there we go. So the question is, do they sound as good as the Genelecs? Maybe not 100%. Do they sound good enough to mix in Dolby Atmos and get a setup going for less than $2,500? Yes, they do, and that's what we're gonna build today. The Sound Sleuth 7.1.4 mixing setup, and here we go.
This is a complex project, but let's break it down because that always helps. First, there's you, the mix master. Then we need 7 ear level speakers. If you already mix in stereo, you have your main pair. Now for height, we need left-right front and left-right rear speakers. The dot 1 is our subwoofer or LFE. Now we have our Mac or PC, an audio interface slant monitor controller, which is essentially a 12-channel volume control, and a 12-channel amplifier. Now we have to connect things. We come out of the audio interface line level into the amps. The LFE is also line level. Finally, we have all the speaker cables. The ones in green are permanently mounted in my room. The blue ones are heavy-duty cable that can be coiled up and stored when not in use. See the Instructables for more details. The speaker build part is pretty straightforward, and there are lots of YouTube videos specific to the Dayton Audio C Notes. I went into production mode on these. I built the boxes a pair at a time due to the amount of wood clamps that I own. See the Instructable for tips and tricks. I did two things different from the stock kits. I used speak-on connectors for all the speaker connections, and this makes life so much simpler. Trust me on this one. Second, I 3D printed the port tubes to ensure that they are all identical. The file for that is in the Instructable. I coated the boxes in shellac prior to painting to seal the MDF, and I'm very happy with the results. The subwoofer is my design. It is an isobaric sub, meaning that there are two woofers used in it. They are separated by a small chamber. This gives us a couple benefits. Box volume for the acoustic properties I wanted is cut in half, making the whole thing much more compact. And because the woofers are wired in parallel, the overall impedance is 4 ohms, which lets the plate amplifier reach its design power output of 300 watts. This is a sweet little sub, and it delivers. It also blends really easily with the entire system with no weird frequency responses. I spent most of this build video on the amplifiers and then the system setup, as those are the key parts of this project. This is the 12-channel amp build for my Sound Sleuth 7.1.4 rig. I started this adventure with a completely different concept using Class D amp boards. I go into further detail as to why they didn't work in the Instructable. Let's just say they had major EMI issues. Having used the LM3886 before, I knew it would work. I kind of wish I started with it. This is the LM3886, a power op amp specifically designed to be an audio amplifier with great specs and capable of providing 68 watts of power. It is an 11-pin chip and a TO220 package with an isolated case. That means we can mount it directly to a heatsink. Let's look at the datasheet schematic and then a couple changes I made specific to our needs. The schematic is a textbook non-inverting amplifier with a 1K input resistor and a 20K feedback resistor. Note CI connected to the 1K input resistor. This AC couples the amp with a 3 dB down point of about 7 Hz. It also requires a connection to ground on the non-inverting input of the amp via pin 10 and the 10K input volume control. There are two capacitors that buffer the plus and minus power supply rails for stability. They're labeled CS. They stabilize the amp and provide a current reservoir so the amp does not motorboat. Then we have a mute circuit. This is a capacitor labeled CM and a resistor called RM. Interesting to me, they call out a 100 microfarad capacitor but no value for the resistor. The default is about 1K. Now we get to the two output protection circuits. The first is a 0.7 microhenry inductor in parallel with a 10 ohm resistor. This protects from capacitive loading of the amplifier, specifically with a long speaker cable attached but no speaker. At high frequencies, the inductor's impedance goes up, allowing the 10 ohm resistor to decouple the amplifier from the load. This happens above a megahertz and will not affect the audio range, but it will protect the amplifier. The second is a Zobel network consisting of a 0.1 microfarad capacitor and a 3 ohm resistor. This protects the amplifier from no load connection at all and the output potentially ringing. The 3 dB down point of this network is about 500 kHz, so once again, no effect on the audio range. I am adding both of these to ensure that this thing is bulletproof. Here's the as-built schematic. First, we do not have an input volume control, as this is handled by the monitor controller functionality of my audio interface. I also got rid of input capacitor CI, making the amp DC coupled and giving us our ground reference. The mute resistor is 20K, which when combined with a 100 microfarad capacitor gives us about a 1 to 2 second time delay for unmuting when powering on the amplifiers. Both CSs are 1000 microfarad capacitors in parallel with 0.1 microfarad capacitors. This is standard practice, as large electrolytic capacitors have a decent amount of inductance associated with them and a pretty high ESR or equivalent series resistance. The small film capacitor helps with any issues caused by that. I'm using a 3 ohm resistor versus a 2.7 ohm resistor, as Mouser carries the 3 ohm resistors, and it totally works. Let's look at our printed circuit board. Full disclosure, I didn't design this, but it has features I really like. Things like thick traces, power lines meant to daisy chain between multiple boards, and it uses a ground plane. It is also available as a shared project on PCB Way. It does lack the two protection circuits, but we're going to add those externally. Please see the Instructable for more information. When I sourced the printed circuit board, I had them make it with 2-ounce copper. What that means is that the traces are thicker, they'll carry more current, and they'll dissipate heat better. I mentioned that the board uses a ground plane as well. That means that all the available space not normally used is filled with copper and connected to ground. This also means that soldering the components that connect to ground is more challenging, requires more heat. And we will see this as we build them. This is the bare printed circuit board for the amplifiers. I changed both the 1K resistor for the mute function and the 22K feedback resistor to 20K. See the Instructable for an explanation. The next thing to note are the polarity markings for the electrolytic capacitors. The white semi-fill on the PCB is the negative side. This will match with the capacitor. Note, if you put an electrolytic capacitor in backwards, it will explode. I have verified this more than I would care to admit. Now on to soldering. The printed circuit board is 2-ounce copper fill board with a ground plane. This means we will need more heat than usual to solder the components. All the capacitors have one connection to ground and a few of the resistors as well. That one side will be difficult. Patience in turning up the heat on the soldering iron helps. Solder the resistors to the board. These are the 1K resistors and are in the signal path, so should solder easily. Oops, got a little solder bridge. This cleans up easily. Now the 20K resistors. All of these have normal PCB traces and solder easily. Now on to the 1000 microfarad capacitors. These are polarized. The long lead is positive and the capacitor body is striped for negative. These are the hardest components to solder as they both have one lead to a large ground plane which pulls heat away from the solder joint. The outside connections are the plus and minus supply rails and the inner go to the ground plane. You can see how much longer than normal they take. And look, it still isn't connected. Let's do the easy one first and come back to the hard one. Flip the board over and inspect. Next up, insert the 100 microfarad capacitors and solder them. They're easier than the 1000 microfarad capacitors and I won't bore you with the actual soldering. Let's mount and solder the actual LM3886 now. There are 11 pins, and this one is actually pretty easy. I like to use some solder on one pin to hold the IC while I solder the rest. This one goes really smoothly. Flip the board over and inspect. The 0.1 microfarad caps go in next. These are not polarized and are in parallel with the two 1000 microfarad capacitors. See the Instructable for a full explanation for why we are using them. Two of their leads are going to that large ground plane and are a bit of a challenge to solder. A wiggle test helps here. Final printed circuit board component is a small jumper wire. This goes in pretty smoothly as well. Clean the printed circuit board with isopropyl alcohol and inspect. We have two protection circuits that are not included on the printed circuit board, but in my mind are mandatory. The Zobel network is a 0.1 microfarad capacitor in series with a 3 ohm resistor. Prep this by connecting them as shown. Now the RL output filter. This is a 10 ohm resistor with an approximately 7 microhenry inductor wound around the resistor. We are taking about a foot of magnet wire, stripping one end by scraping the insulation with a razor blade, then wrapping 10 turns around the resistor. Now cut the excess wire, strip the insulation, and connect it to the other end of the resistor. Old school, my friends. This is old school. Now let's add the input and output wires with the protection circuitry. Prep a 2-foot piece of mogami wire by stripping the end, twisting back the shield, cutting back the white internal wire, and stripping the end of the red wire. The wire needs to be long enough to go from the board to the XLR inputs on the back of the rack and have excess for some nice wire management. Tin the input and output connections on the printed circuit board input section. Tin the shield and the red conductor from the mogami wire and solder that to the input connections. Now we're going to insert the RL filter and solder that to the printed circuit board. This goes into the out connection. Prep the speaker connection wires by twisting 2 feet or so of black and red 18 gauge wire. These need to be long enough to go to the speak-on connectors on the back of the rack. Strip and tin the wires once twisted. Prep the RL filter connection by forming a small loop in the resistor lead and tin with solder. Solder the red wire to that. Now connect the black wire to ground via the printed circuit board ground connection. The last step for the printed circuit board is to attach the Zobel network across the speaker output connections on the printed circuit board. Take a break and inspect your work. You only have 11 more of these to build. There are a few things that we need to take into account when turning the 12 printed circuit boards into a full-fledged system. And they are the power supply, turning it on and off, input connections, output connections, and the case. Let's start with the power supply. The LM3886 needs a dual supply. We're using two 36-volt switching supplies that can provide about 10 amps each. You must take appropriate precautions here. First, there's 72 volts DC across both the power supplies, which can and will shock you. Second, there's a large amount of capacitance across the supply rails. This stores a lot of energy, and if you short this out, it will arc and it will weld whatever caused the short to whatever it touched. Seriously, ensure that you know what you're doing or have someone assist you. Remember Ready Kilowatt? He can kill. We're also connecting the line voltage with wire and screw terminals. If you're familiar with this, great. If not, please find a friend who is. On the AC side of things, we need to connect the AC inputs to a power cord and then jumper the first supply to the second. Electrical code in the US is white neutral, black line, and green ground. On the DC side, we designate one supply as the plus supply and the other as the negative supply. Connect the plus of the negative supply to the negative of the plus supply as shown here. Basically, we are wiring them in series with the connection point becoming the DC ground common point. These supplies have a voltage adjustment potentiometer on the left side. Ensure that both are set for 36 volts. To turn the amplifier on and off, we're not going to switch the AC side of the supplies, we're actually going to switch the DC side to the amplifiers. To do this, we're going to use two 60 amp relays. We will need 12 volt DC to do this, so we're adding a 12 volt regulator to supply it. The one that I spec'd out is a buck converter and it is adjustable, so we need to set it to 12 volts. To do that, connect the inputs to a 24 volt or higher source, a multimeter to the output, and then adjust it for 12 volts DC. This gets connected to the positive rails power supply. The output of the buck converter goes to the toggle switch and the two relays as shown so that they both turn on when the switch is closed. One relay is for the positive supply rail and one for the negative rail. The output of the relays go to two WAGO lever nuts for distribution to the amplifier boards. The ground rail does the same. I used three 5-terminal WAGO lever nuts that I glued to the bottom of the rack case. This let me double check the polarities of the power supplies prior to connecting the amplifier boards. Once you have this tested and verified, let's move on to the amplifier modules. The LM3886 needs a heatsink. It's a class AB amplifier, meaning that it produces some heat. I already had enough heat sinks to build my amplifier, but I found ones of the same size and thermal properties on Amazon. They are 100 by 50 by 30 millimeters and made of aluminum. You're going to need 6 of them. Each one gets 2 amplifier boards, and then the 3 of these assemblies mount to a 12-inch piece of aluminum angle. All in, we have 12 channels of amplification. To mount the amp boards, we hold them in place and mark the spot to drill and tap an M3 screw. Note that the printed circuit board extends a bit beyond the LM3886, so you'll need to mount it accordingly. This shows the 2 mounted on the heatsink. You will also need to drill and tap some holes at the bottom of the heatsink so that can connect to the aluminum angle. Now we need to connect the amplifier power connections. Use 18 gauge wire to daisy chain the amplifier boards as shown. Then from the board on the end, solder 18 inches of wire to the plus, minus, and ground connections. Use color-coded wire as we're going to braid them to keep things tidy, and for that little bit of extra EMI protection. Mount them to the bottom of the rack. We don't want these moving around while testing. Cut the power wires to length, strip and connect them to the WAGO connectors. Double check the polarity as you do this. The input and output connections. Mount 12 XLR female connectors to a single rack unit panel and 12 speak-on connectors to the other single rack unit panel. Starting with the output panel, solder the speaker wires to the speak-on connectors, red to 1 plus and black to 1 minus. The connector's labeled and you must pay attention to polarity. If you think having a speaker out of phase with stereo is bad, try 1 in an immersive audio setup. Take your time and dress the wires in as you go. After these are connected, take a break and visually inspect your work. Now on to the input connections. These are standard balanced XLR connections and we are going to the amplifier boards unbalanced. Prep and solder the Mogami wire as follows. Shield to pin 1, red to pin 2, and white to pin 3. Jumper pin 1 and 3 at the XLR connector. Ensure that the input and output connections line up one above the other as you connect the next 11 XLR connectors. Take a break and inspect your work. Now mount the 2 panels to the back of the rack case with the XLRs on top. Let's test it. For testing, you can do a couple things. You can use any stereo source as long as you can adjust the output level and 2 of the speakers. Go down the line and test the amps in pairs, or you can test all 12 at once. As this is my 3rd go around, I already had my speakers set up and I tested them all at once. Once you know that everything works, it is time to finish the enclosure and put all the equipment in the rack. If you remember, I started this whole thing with the intention of having the 12 amp channels and a 2 rack unit case. This is what that looked like. Then, with my inability to get multiple channel Class D boards working together, I tried 2 6-channel boards and then 3 4-channel boards with different chipset. I ended up where we are now. The amps all mount to the bottom of the rack case, but I had to add a shelf above them to seal them up, a front panel with a toggle switch, and then 4 risers in each corner to support the shelf. Finally, I added a 1/2-inch plywood panel on the back to close it off and to feed the power cord through. The power cord has a clamp on the inside to hold it all in place. Alright, the hard part is complete. Let's get this thing configured, set up, and start mixing.
We've got our system built, 7.1.4. Now there's a couple things we need to do to get it rolling and working smoothly and integrated into the studio. We need a monitor controller, which basically is a 12-channel volume control. So we have to go into the Focusrite and set that up. I'll show you how to do that shortly. And then the other thing we need to do is match levels in the room. I'm going to say something here, it's a little bit controversial. I am not calibrating this room, and as you can hear from my voice now, it's not acoustically treated properly. It will be, that's my next project. But as you can hear, it's really not dead and it's not the best room ever. However, with these speakers are set up, they envelop you and the sound is just amazing. I can't describe it, and if you live near DFW, reach out to me and I'll have you over and you can listen to how this thing sounds because it's amazing. Okay, so now we've got our monitor controller set up as our volume control, and then the only thing I really did was match levels on all the speakers. As you can see, my mains behind me, they're more sensitive than the Dayton C Notes, so I had to make adjustments to the Dayton C Notes, about 4 dB for the ear level surrounds, and then about 6.5 dB for the height speakers because they're a little bit further away. So that's all we had to do. Oh yeah, and a little bit of adjustment for the subwoofer. I think I'm up about 4.5 dB on that. So let's go set this up, see how to do it, get Reaper all configured, and after that, we can start mixing.
Setup and calibration. I am not fully calibrating this or getting it certified to Dolby Atmos. The bulk of the audio engineers I've discussed this with turn off the Dolby specific calibration settings after the Dolby engineer leaves. And some of these guys are world-class Grammy-winning engineers. How many of you EQ your stereo setup? How many of you move your speakers slightly and measure 60 degrees between you and each speaker? There's a lot of material out there for tuning your room, acoustically treating it, and setting up the sweet spot, etc. The critical thing I've learned for immersive audio is that we need to level match the speakers and get them positioned so that you can put those positions into a couple different plugins when decoding. Dolby tries to be very specific on the mixing setup, and then they patent a consumer playback system that does this. Bounces the sound off the ceiling for height, which does work, but I would throw out there is not very scientific. What is the actual living room ceiling height? Is that soundbar shoving under the TV set? What material is your ceiling made of? Who knows? The first thing we need to do is set up the Focusrite interface to be a multi-channel volume control. So we're going to go to the monitoring section, and by default none of this is selected, and all we need to do is check all and hit apply. And now when we adjust this monitor level control here, or more importantly the front panel control, all of the other levels for the outputs from 1 through 16 will change. If you're using, say, outputs 13 and 14, 15, 16, for something else, maybe hardware sends, you can just turn those off and apply, because all we really need are these that are linked. So this all will get all of them, or you can individually select which ones are going to be used. And that's it. We've got it going. Okay, now what we need to do is set up Reaper so that it is fully set up for a 7.1.4 immersive audio setup. There's a couple things that we need to do. The first thing is we're going to rename the output channels so that we know where they are. So we're going to go into settings, audio, and then output channel names, aliasing, remapping. And you can kind of see I already have done this, and the way it works, so I've got left, right, center, hardware 1, 2, 3, 4 is a subwoofer, 5 and 6 left and right surrounds, and so on till we get to 9 through 12, which are our height speakers. So the way this works is, you click into one and the alias name is blank, and you can put in whatever you want. And when you click OK, it changes there, and you click OK on that, and now output 13 is named after me because, that's how it works. Okay, so that is naming the output channels. The next thing we need to do is on the master channel routing, Reaper defaults to stereo or 2 channels. We need to make this 12, and then we need to come down and send our multi-channel source out to 12 channels, 1 through 12. There you go, and you can kind of see left, right, top, rear is all the way on the bottom for the 12 channels. Now, to get the levels of my speakers properly adjusted, Reaper provides something called monitor effects. So if I go to the monitor effects, I have already added 12 channels of RIA EQ to this, and we're going to see how those are set up. So for the left channel and the right channel, you can see I've got no gain settings and really no EQ settings. But the key to how this all works is to go into our plug-in pin connector. So I've got, you know, this is channel 1, which is our left, so it literally goes 1 to 1. And then if we go into the second one, look at it, that's right. So we get, you know, 2 to 2, and then I'll just jump ahead all the way to one of the height speakers and look at that, and we get 11 to 11. The other key thing with this, it's done this way by default, but you want to double check, is on our IO settings that you have it set to multi-mono, which means the EQ in theory could be 12 channels and it could affect all of the 12 channels. That's where the plug-in pin connector comes in, so it's only affecting 1. And then we want to pass through the unmapped output channel so that it doesn't affect any of the other output channels. And that's it. That gets us set up to send our audio through Reaper, adjust it as needed for the room. But if you render this out, none of those monitoring effects will apply to the rendering. So that's it. We have Reaper set up. Oh wait, I'm sorry, one more thing. When you add a channel for editing, it too, like the master channel, will come up as a stereo channel by default. So right now we're sending channels 1 and 2 to the master send, and there's only 2 track channels. We are going to do immersive, which means we need probably 12 of these. So we just go to set that to 12, send to the master channel, and now we're good to go, and we can add in whatever effects we need to mix in immersive audio, which brings us to that section of this video.
All right, we've got this thing set up, we've got the level set, and we're kind of ready to go and start mixing. There are 2 concepts that you need to know for mixing in immersive audio, and those are beds and objects. So beds are kind of just default audio track channels. So if you think about stereo, a stereo bed is literally the left and right and none of it changes. And if you have a surround sound mix that's a bed 5.1, 6 discrete audio channels, and that's how that works. Objects, on the other hand, can be mono all the way through as many channels as you have. But the other thing that's associated with an object is metadata. So basically you're taking, say, an object like a snare drum, back in the day, saying when the Beatles mixed stuff, you pan the snare drum hard left, right? So the left is 100% left, 0% right. An object, if you were to do the same thing, would have the audio file for the snare drum with the metadata saying 100% left, 0 and everything else. So the reason that we do objects in immersive audio is you don't know what the playback system is going to be. So if you set up an object that you want, I want my left and right audio to be kind of halfway between the front and the rear, kind of in the sides, instead of just routing it discretely to, the left and right side channels, you would put that metadata in there, and that way if the sound system upon playback is 714, it'll put it where you think. If it's 9.2.6 or 22.10, or if you're lucky enough to play at the sphere, which can almost do anything, the metadata with the objects will tell the system upon playback, and that's the key. This is rendered upon playback. So it's kind of like having a mixing engineer in a box, and you're telling him to pan this thing here, this thing there, put this thing over there, and you cross your fingers and hope it gets done that way. Which is one of the challenges with this, because we've seen many people, they mix something, they submit it to Apple Music, and it just doesn't sound right. upon playback. And that's because Apple Music has decided how they want it rendered upon playback and made some decisions for you. So with immersive audio on the mixing standpoint, there's a ton of material out there. My big awakening moment for you is no one's figured this out yet. We're all still working on it, and this is your chance to go do it. But there are 3 setups that I want to talk about in Reaper of how to mix things, and these are just starting points. By no means at all how you're going to end up doing it. So there's literally the discrete thing, right? We have our pan pot. Back in the day, that was, you move the pan pot left, you move the pan pot right, and the signal went from left to right. What does a pan pot look like in immersive audio? What does that mean, right? So that's one thing to think of, how that's going to go. And then the formats that you're going to do this with is you're going to kind of get a mix set up, discreetly in the bed type of scenario where you're mixing through your digital audio workstation of choice. I like Reaper, that's what I'm working with. But basically you set everything up so it sounds great in the speakers, and then what do you render it to, right? Do you render it down to a 12 channel broadcast wave file? If you do that, you can send it to people and they can use it. It's kind of cool. But you can't send that to Spotify, you can't send that to Apple Music, and you could burn it to a Blu-ray as a data file, but this isn't quite figured out yet. We're still working on it. Or we go the Dolby Atmos route. I use Atmos Composer from Fiedler Audio. I really like it. There's some unique things about this when you put it into the signal chain. There's 2 parts of that plugin. There's a Atmos beam that basically takes your incoming signal on the track channel and you tell it what you want it to do. And then there's the composer part of the plugin that's kind of on the master bus, kind of bringing everything all together. Because if you think about it, every digital audio workstation out there from the ground up has been designed to be stereo. I think Pro Tools only a couple years ago went to more than 16 tracks on one channel, right? Reaper went from 64 to 128. You've got Apple Logic, you got all these other ones. They were all written from ground zero to be stereo. And that's not how the world is anymore. So we're all trying to figure it out. I'm gonna go through these 3 methodologies and then you take it from there and mix the way you think it should sound good and experiment. Nobody has this figured out yet.
So, how do we use this thing? Scenario 1, you just mix. Originally we had stereo. So you bring a signal in, then you have a pan pot. Yeah, you can put effects on the mono signal up front, say an EQ or a compressor. Then you pan it in stereo. Maybe add some stereo effects. Or, you send it to an aux bus for reverb or delay. But WTF? What is a multi-channel pan pot? Do you know, just rotate through the settings and have it sent to each channel? No. You need to use an immersive panner. And moving things around is like keyframing an animation, as you need multiple parameters. You can still use aux buses going to reverbs and delays, but even those need to be treated totally differently. Then upon rendering, do you output a multi-channel broadcast wave file? You might if you're doing a sound installation or something very specific. Scenario 2, using higher order ambisonics. This is the behind the scenes of how Sony 360 and a couple of other standards work. One challenge is to ensure that you don't send the audio to the master bus until it is decoded into what every speaker array you have. This is one huge benefit of ambisonics. I did my first order Ambialis about 3 years ago. It wasn't until I had this immersive playback system that it truly amazed me. But there are things to keep track of, such as formatting, what position the microphone is when you recorded it, what kind of, are you using AmbiX, Fuma, whatever. There's a bunch of things that you need to keep track of or it just won't sound right. Scenario 3, Dolby Atmos. This is where you assign things to be objects or beds. I'm using Atmos Composer from Fiedler Audio. There are 2 plugins, an Atmos beam on each signal and the Atmos Composer on the master bus. In essence, this plugin resides outside of the normal DAW routing. It ignores panning and level settings for each track. You can put plugins before the beam, which is good, and it also renders outside of the normal method. I encourage you to play, learn, and experiment. One thing I can tell you is no one has this completely down yet. until songs are composed and recorded with the mindset, if I'm going to mix this immersively, we truly won't have it figured out, and the future is wide open, and I'm looking forward to it.
All right, this wraps up the Sound Sleuth 7.1.4 system mixing station, whatever you want to call it, build video. This is the longest YouTube video I've ever put together. I started working on this at the beginning of the year, and I am just thrilled with the system I've got. And it's opened up my ears to a whole new way of doing things. Hope you enjoy it. Get out there, build one, and start mixing in immersive audio yourself. Thanks.